Hi, this is Tariq Rashid. Today I am explaining a new algorithm which is called Fitness Dependent Optimizer or FDO. FDO, Fitness Dependent Optimizer, is a nature-inspired population-based metaheuristic optimization algorithm. It is inspired by the bee swarming reproductive process. Actually, swarming is mostly a late spring phenomenon. It is the process by which a new honeybee colony is shaped. The queen bee tries to leave the old colony with a group of worker bees and some scout bees. The swarm basically consists of 1,000 to tens of thousand bees. They manage to settle 20 to 30 meters away from the natal hive temporarily. Queen bee then sends 20 to 50 scout bees out to find appropriate new hives. Usually this takes several attempts with the guidance from the scouts, and the rest of the bee or bees flying overhead in the proper direction. So this table shows you that what we have in nature and what is equivalent in the algorithm. So scout bee means search agent, hive means solution discovered, so on and so forth. Now, FDO is a particle swarm optimization based algorithm, but it is completely different from it. Now, FDO, it has its own nature behavior and fairly simple and easy to understand. This equation is the backbone of the algorithm. That's the current solution. This is the next solution. It's the current solution plus the pace. And pace can be found by this equation, which is equivalent to the current minus the globe times fitness weight. And fitness weight can be found by this equation, which is global fitness over the current fitness. Now, this is the same equation, equation one, which was explained. This is equation two, which is the fitness weight, how it can be found. Actually, the absolute value of global fitness over the current fitness minus weight factor. Weight factor to control the fitness weight. So this perimeter weight factor actually is it's either 0 or 1. Now we have more equations, equation 3 and 4 and 5. I have to say these equations depend on the conditions that we have, and these are the conditions. So if you have this condition, you would calculate base in this way. And if you have these conditions, you would either use this equation, or if you have these conditions, you would use 4.5 to find the base. Now, R, basically, this R, it is in between -1 and 1. So R randomly generated between -1 and 1. If you have a maximization problem, then equation 2, which was this one, reverse of equation 2 can be used for maximization problem. So the algorithm works originally for minimization, but if you want to do maximization, you just have to flip this fraction and minus the same weight factor. So that is the only difference, plus another more difference. So this if condition will be replaced by this if condition. So this if condition will be replaced by the condition. Now this is the pseudo code for the algorithm, and this is the flow chart. You can check it and work on it, and it is there for you. Now, the algorithm used for single objective optimization problem and multi-objective optimization problem the algorithm has been used for aperiodic antenna array designs, frequency modulated sound waves, and for multi-objective, there is an application welded beam design engineering problem. Now, the algorithm outperformed the current competitive algorithms such as PSO, genetic algorithm Dragonfly, multi-objective Dragonfly, multi-objective genetic algorithm, and multi-objective PSO. We have one case study so that we can show you how to use this algorithm or how to understand the physicality of this algorithm, how to implement it in the future for your different applications such as health application, energy, control, electrical, construction, education, etc. So we have table 4.1. This table has parameters, parameter 1, parameter 2. We have 50 values of these parameters, parameter 1 and parameter 2. Actually, this example, we will take 3 bees, 3 agents. Each one of them has 2 dimensions, x1 and x2. You can have many dimensions, but this one only for learning. So, and the fitness that we selected is xi squared, sigma xi squared. Okay, and the d you decide. For this example, we said we have only 2 dimensions. So for the first bee, you can have, for the first position, you can have r multiplied by upper bound. For the second bee, r multiplied by lower bound. R is random, and upper bound and lower bound are given 100 and minus 100. So here for first iteration to calculate the parameters. So first B, we take this value and this value, minus 4.9 and minus 4.7 from the table. That's minus 4.9, minus 4.7. And for the second B, 0.44, minus 48. And for the third B, minus 22, minus 52. So this is the result. So the fitness for the first B, it is this much, okay? Because we calculated, we get the position for the first B, and we put them in the fitness function, and we got this one. For the second B, same thing. We get the results from the table. These parameters are given, multiply by the upper bound and lower bound, and get the fitness function, fitness for the second B. Likewise, for the third B, minus 22, minus 52, get the values, multiply them by upper bound, lower bound, and get the fitness. We can see that we can notice that this one is 4,610, this one 8,020, and this one 3,188. This is the minimum that we have, and we do minimization. So this is the fitness function in this iteration. This is the best solution that we have. So the best solution we have minus 2252, and its fitness is 3188. That is the third agent. So the third agent, that one was the minimum. So next iteration, we will try to get use the rules to get the fitness weight, and we have to rely on the pace, okay, and to get the next position. So we need to get fitness weight and the pace, and then pace, plug it here, get the next search agent. That's how it works. So we will find fitness weight for the first B, which is the best fitness over the current fitness. We get 0.69. Through the 3 equations that we have, we randomly toss R between -1 and 1. we get this value, and we try to get the new position for B1, and for the second dimension for B1, new position. So these are two values. We plug them into the equation 1, we will find the new position for B1 and B2. And we plug them into fitness equation. We will find the fitness for the B1, search agent 1, this much, 9,414. This is higher than the global fitness that we have in the first iteration. So we will keep the previous fitness function that we have, fitness value, because 3188 obviously is less than this one. So we are not going to change. For the second B, we have the current global, we haven't changed it, global fitness over the current B, second B. We get this one. We, again, randomly we select R for second B for the two positions, and we get their values. Now we plug in the values of pace, okay, pace 1 and pace 2. We get the values for them for the second B. Now we plug the positions, the current search agent for dimension 1 and dimension 2, and we get the fitness value. And this fitness value, again, unfortunately, higher than the global fitness that we have, and it cannot, it will be ignored. So the fitness function stays, fitness value, global fitness value stays as it is. Now we are going to work with the third B, which has, we have the global fitness is 318, and the current fitness, the third one, it has the same. So the global, the agent, it is the best agent, and it has the same fitness as it is the best. So therefore, FW, fitness weight, is equal 1. And now, randomly, we select R, we get two positions, two paces for the third B. They will be 0, 0, because actually the current equals the globe. Current equals the globe. So now the fitness that we have it in this iteration, which is the second iteration, is higher than the previous fitness that we have. Therefore, the global fitness has changed in iteration 2. And if we have the table, you can see the fitness has been changed. 0, 0 is less than the previous one. Therefore, this is the iteration. You can work out third iteration. That's the basic idea how the algorithm works. And if you have any problem, you can always contact us. Actually, the algorithm, you can, the code for Java and MATLAB can be found in here or in GitHub. And always you can call us in our in my email addresses, and you can always find more information about different algorithms that we have them in this link. And if you have anything, as I say, you can call me in the following email addresses. Thank you very much for listening, and I wish you all the best. And thank you. I wish you all the best. Thank you.